Good day from Oakville, Ontario, Canada. It's my pleasure to be here today to talk to you about best practice comminution. And I'm pleased and excited to be invited to talk about this subject today. This is the outline of my presentation, and it includes 9 topics as shown on the screen, and followed by acknowledgements, because there's a lot of things that happened that were very helpful to me in the work that I've done over the last 30 years. The keys to best practice comminution. There are 3 reasons for this presentation: so that operators can manage good process plants and do it properly, so that designers can produce workable designs and include the features that are expected of a modern day SAG mill operation. And third, that educators provide useful education and information to not only university students studying mineral processing, but also to the operators who are going to run the plants that the designers build for them. The term best practices is overused. We've heard it for the last 30 or more years, and people claim to know all about everything. So we should know something about this. But really, I have to ask, do we? SAG milling has been in our industry in Canada for 70 years or more, and it's always been presented as proprietary technology with the details obscured. We have to ask, why is that so? Is this in your best interest as somebody working in the industry, or is it in the interest of the person providing the information? Make no mistake, a SAG mill is the heart and soul of every mineral processing plant that uses a SAG mill. Canada has seen many problems and massive financial losses in the last decade, and this talk should address some of the things that have caused those problems. As an industry, we need to attract sharp young engineers and always use best practices and immediately upgrade the teaching that our students in university are getting. It is unthinkable that a person can graduate from a university today and not understand how a SAG mill works or how it is designed. So in this talk today, we need to make choices and decide what to talk about. Are we going to talk about myths, unproven theories, preferred choices, or facts? I think facts are the important thing here. The goal of a mineral processing plant and a SAG mill is to make profit for a client mining company. And I submit that every engineer who works in this field needs to know how to design a SAG mill. So right off the start, we need to decide the test and design method. So rather than me tell you what's best, I'm going to ask some questions, which I think, if the answer is yes, will reveal whether you're on track or not. Does the method you choose to design your SAG mill have a track record that gives good design tons per hour from day one, with no modifications or extra expense to correct the problems in the design? Is the design for the 80th percentile of hardness variability in the deposit? Can grinding test results be krieged in a mine plan? Some results can and some cannot, as was pointed out by Dr. Malcolm Powell several years ago at a previous Comminution conference in 2018, where he pointed out that the JK A times B cannot be krieged into a mine plan. Is easy expansion part of the design? Because if it is, and provision is made to expand, then the front-end engineering cost to engineer the modification can be greatly reduced, and this is an important part of designing a plant, not just for today, but for the future and what we know is going to happen in the future. Can lab and pilot plant grind and beneficiation be done using drill core? Drill core is the key to getting access to good samples and to designing a plant that represents the ore in a deposit. Has high confidence flotation been chosen for the lab work? Because we want to coordinate the grinding with what works for the processing downstream. Now, a key point that is violated in most operations is, will the plant run at fixed tons per hour and at the proper grind? These are key points. Do they make for a bigger SAG mill? Of course. If you cut corners and scrimp on the most important piece of equipment in the plant, it's going to cost you money in other ways. So I think we need to respect the engineering specification for a plant. If it calls for 1,000 tons an hour, then that plant should be able to run at 1,000 tons an hour all day, every day. These are the criteria for best practice comminution. Simulation without good kilowatt hour per ton hardness data, in my opinion, is now obsolete. It was okay before to consider that when we did not have accurate measurements of SAG hardness in kilowatt hours per ton. But because we do now, we shouldn't be comparing with other plants to decide whether this plant is okay, because simulation used that way propagates negative step changes if the mills are too small. We build a new mill and compare it to mills B and C, and if they're too small, then mill A that we design is going to be too small also. So I submit to you that only hardness information from a client's own ore body should be used to design his SAG mill. We need to do design work remotely in every plant, not just approach the professionals to do it, because people might be working in the Northwest Territories and the manager wants to expand his production and replace a crusher rod mill system with a SAG mill. His engineer should know how to do that, and he should not have to go and seek professional advice as to what. Oh, sure, to do the final design, professional advice. But in order to get the project started, people have to be in the game. And that's not happening today, and it's wrong. Best practices, test measures, SAG kilowatt hours per ton to 1.7 millimeters, and the bond work index on SAG ground ore. It's interesting to note that when Bond did his tests, he knew that rod mill hardness was not going to be the same as ball mill hardness, and so he did both. And this is even more pronounced when we talk about coarse grinding hardness in a SAG mill, because the difference between SAG hardness and ball mill hardness is so vast in some cases that it just cements the truth that you need both the coarse hardness measurement of energy and the bond work index in order to understand how to design your SAG mill, ball mill circuit. Years ago, when we were designing crushing rod ball plants, it was expected that you have 10% extra tons per hour in the circuit. But we've lost that with SAG mills. Now we figure 15% less is is okay. And many consultants in Toronto, for example, thinks that that's how a mill should be designed, to save money on capital. This is nonsense, because the saving in the size of the SAG mill may be $2 or $3 million, but if you're racking up 250 million in lost production in order to save that money, it makes no sense at all. There's some indicators of good performance. For example, the capital feasibility study estimate is met and no additional funds are needed in order to get the mill up to full production. The operating costs are equal or lower than predicted in the feasibility study. Design tons per hour are achieved every day, and grade control is used to meet the budgets at the design cutoff grade. If you start changing the parameters of revenue and cost, really the whole financial structure for the project changes, and the cutoff grade should be adjusted, which plays with the value of the ore body. And if a mill is deliberately designed under production, then you're using the client's resources to fund the bad design. And that just is not right in anybody's sensible assessment of the project. Annual tons in the feasibility study are met. And when this is done, if a manager wants to spend some money to make improvements, he'll get head office support for the money to do his project. If he's not even meeting target production, head office is not going to do that. So the project becomes stuck in limbo with no way forward. The fineness of the grind will be the same as the design liberation and confirmed by pilot plant. Lastly, the control room will be a comfortable and harmonious place to be, where people sit down for a morning cup of coffee and talk about what's going on, and maybe spend a few minutes talking about the weekend and taking pride in their work. I think it's a big mistake to forget that part of an operator's life. The role of T80 in SAG mill design. This has been and will continue to be a point of contention until we recognize what's causing it. The failure of the JK software to include T80 creates a misconception. JK software was built on massive, well-organized research programs to do optimization work in an existing plant, not design work. The taking of the design work from JK software and then using simulation to compare it with existing plants is just, and I'm sorry to say it, it's just not best practice anymore. Any reasonable T80 can be used from 0.1 millimeter to 3.35 millimeters. Bear in mind that the feed to a bond work index test is 3.35 millimeters, 100% passing 6 mesh. And so the bond work index only applies up to that size. When we start extending beyond 3 millimeters to 4, 5, 6, and even 10 millimeter transfer sizes, we're actually asking the ball mill and the bond work index to grind coarser materials, of which we don't know the hardness unless you've measured it with a rod mill work index or a SAG test to determine how much energy you need to get down to 2 millimeters. So if you feed a coarser T80 to a ball mill, you can expect inefficiencies, and therefore these should be avoided. Now, these are points are what operators and managers of plants need to know. The people that design the SAG mills for you don't really know or care about whether you're putting 10 millimeter stuff into the ball mill. It's still something that's has the potential to create big problems for your grinding efficiency. To demonstrate what T80 can do, we've put together a little table, which I'll show you on the next slide. We've assumed an ore with a hardness just above average, 10 kilowatt hour per ton, average is 9.4. Bond work index is 15 kilowatt hour per ton. Average for all projects in our database is 14.6. And we want a capacity of 471 tons per hour, which is 3.8 million tons at 92% availability. In general, we need to look at the mill size that results from increasing the screen classification size. So we're going to choose T80s by doubling the screen opening size and calculating the required mills. And we've done this for that example, and here's what the table looks like. Case 1 is a single stage SAG mill or no screen at all. And the mill is 36 by 17.8 feet long and has 14.9 megawatts to drive it. Now, the reason the megawatts are high for the SAG mill option is because SAG milling does not enjoy the same benefits of decreased power at large diameter. So there's a penalty in power to use the coarse mill. But there's tremendous savings in both operating costs and ease of operation to run one mill instead of a SAG mill and a ball mill. That's why the single stage SAG mill should be evaluated as part of any study to pick the comminution circuit for a new plant. We move to 150 micron product size from the SAG mill, and in this case the mill simply shortens, and we make 150 micron transfer size to a small ball mill, shown here as a 15 by 24. And as we go to coarser and coarser T80s, product size for the SAG mill, the screen gets bigger, 5 millimeters with cyclones for the first 3 cases, and then 1.3 millimeter for 4, 2.5 for 5, as the transfer size moves up to 1700 microns, 10 mesh with a 5 millimeter screen. Very similar to the Highland Valley plant at that point. So, and finally, the coarsest is a 3.4 millimeter, and that's a 10 millimeter screen. Now, the problem here is that many manufacturers will give you a 12.7, a half-inch trommel opening. And when they do that, they're really right on the bad side of being too coarse, where scats can get into the ball mill and affect the efficiency. That's why it should be avoided to go over 10 millimeter screen size. So we've studied that table and made some comments. Case 5 is the normal choice, and it would be nice to have the table in front of me now to talk about this, but you can just review the comments here. Cases 4, 5, and 6 are all basically good choices, commonly used, because they all use screens. And a 32-foot diameter mill is a very common size. And if you're choosing between a 30 and a 32, I would just offer the comment that a bigger size is like having money in the bank. You're going to be able to get more throughput in a big mill than a small mill. And if you're going to scrimp and save on the cost of your SAG mill, you're just inviting shortfalls in production down the road. So case 1 is a single stage SAG mill, and the reason it's great is that later on you can add a ball mill and double the production without spending a dime on the conveyors and bins feeding the ore to the mill. Cases 2 and 3 come into play. If you have existing equipment, you want to integrate it into the plant, you can. I don't think people understand that all these choices are available, and it's time that we did, that you can engineer to use existing equipment, that you can engineer for future expansion, and this is part of best practices comminution. Any job can be satisfied by 2 or more SAG mill sizing options. There isn't just one best. There's many options. So when selecting a SAG mill, more diameter paves the way for more tons per hour. And when the T80 is over 70 microns, I recommend using a single stage SAG as a starting point for discovering the possible best economics and to compare with other methods. So let's just summarize best practice operation. The SAG mill is a good choice on any ore, especially for variable ores. Wet feed, clay content, frozen pieces all work well in a SAG mill. Now for super hard ores, where both the SAG hardness and the ball mill work index are 30 kilowatt hours per ton or greater, the energy costs may be out of line, making a crushing option feasible. And because there's no point, I guess the way I'd summarize this is to say that any ore can be ground in a SAG mill, but a really hard ore, you may not want to do that because of cost. Lack of water can also make a SAG milling a hard option to recommend. And this has caused some plants to use dry, air-swept milling in the old airfall concept. But those plants are becoming increasingly rare because of the environmental hazards and the fact that there's a lot of wear cost involved in classifying dry ground ore. Best practices include running the SAG and ball mills at 75 critical speed and the load at 26% for the SAG mill, and probably 33 to 35 depending on the size of the ball mill. In my world, I don't include steel ball additions over 10%. This is because of high wear and cost. It doesn't make any sense to be doubling, for example, taking steel up to 15% when it could be 7.5%, and doubling the cost of the steel when you could have a nice, comfortable operation at just below 10%. And I think there's a lot more studies that are going to have to be done in the universities to prove what's really happening. Of course, you could overpower something and just put it up to 15, 18% steel. But I honestly can't see why that helps, because you're going to wear out your liners quicker, and every time you shut down to change them, you're going to lose production. So rules for SAG mill sizing, some apply, and some designers, including manufacturers, really aren't aware of this. They don't want people, I think, to be aware of what these are. But when you have soft ore with a coarse liberation size, this can be a problem because you need to get the stuff out of the mill. And if you have a long mill, you can't do that. It's going to overgrind before it gets out. So for SAG ball mill circuits, the diameter over effective grinding length should be over 2. And if it's under 2, then you really need to think carefully about why you're doing that and if it's going to work. Ball mills, on the other hand, length over diameter 1.65 is about as long as you should be going, because it becomes a tube mill when it gets over 1.65, and very difficult to get the ore out at a coarse size. So a T80 between 1 and 3 millimeters in a SAG mill is best. The ball mill work index feed is about 2 millimeters, and the SAG design test was set up to correspond to that. So we find out how much energy it takes to reduce the sample to 80% passing 1.7 millimeters. And that's the thoughtfulness that had to go in to make the SAG design test as attractive as it is. In single-stage mills, almost any configuration will work. It could be short, square, or long, and it's going to work fine because a sag mill is the most forgiving piece of equipment in the plant. And it's remarkable that it is so. Maybe they're going to have to add steel down the road to their ag mill. And so if you're spending $10 million on a mill, you should spend the little bit extra to get a thick enough shell to support 15% steel, not the 5% that an ag mill is designed for. So sag mills make coarser product as the steel load increases. The autogenous work index from a Ferguson test is something that really needs specialist input, and you shouldn't touch it unless you're a specialist, because that test is done at 45% load and really is not relevant to most situations. We now have pilot plant testing of underground ores. For 70 years, SAG pilot testing had not been done. The East Kempville was an example where they tried to do regular 6-foot diameter SAG mill testing. They drove and added into the ore body. They did the testing at Lakefield, but the ore was discovered after several years of production not to be representative. And on top of that, the results came in too late. We couldn't include the SAG mill in the plant anyway because it had already been designed with rod mills, and the SAG results arrived 1 month before the issue of the feasibility study that was used to build the plant. But it did prove that small scale tests are needed to measure ore hardness variability. Actual pilot plant beneficiation work was done using ore crushed to 10 mesh. This is what people do now because they can't test sag ground ore. They crush it to 10 mesh and do their beneficiation in a laboratory pilot plant ball mill. So there's no sag has ever been used up to this point for underground ore where you can't get 6-inch pieces to put in the pilot mill. But flotation chemistry is an important part of what's going to happen, and so this has been a detriment up till the present time. This problem, I submit, has been solved now with the introduction of a 1.6-foot diameter mini pilot SAG mill. This graph was presented at SAG 2019 in Vancouver, and the significance of it was missed at the time, but the blue grinding energy reduction curve on the right is crucial to pointing out what we can do with this test now, because the energy that we indicate by using a test that's crushed to 80% passing 3/4 inch is still on that straight line. And I submit that this is why the SAG design test works so well, and it's why the mini pilot SAG mill that uses the same size chamber as the lab mill and the same size feed, 80% passing 3/4 inch, is going to be perfect for doing beneficiation work on SAG ground ore in the new pilot mill. It's the same size as the laboratory. The patent has been applied for to protect the data which has been generated over 17 years, and it lies on the straight line power reduction graph. Raising the SAG design test feed size to -1 inch is thought to be just above the finest point where representative mini plant beneficiation can be done on the mini pilot SAG mill product. It's sort of serendipitous that it's happened that way, but we need now to take advantage of that. And we're predicting about 10 kilogram per hour of feed on average hardness ore. Let's talk about a path forward. We need to restore confidence in the way plants are designed and built. CIM should be involved, PEO should be involved, because it's professional engineering work, and there's really no work in the mineral processing sector that's more important than designing a SAG mill to the financial health of a customer. The JK optimization tool is excellent, must be retained. It's astonishing that no place to add or use T80 in JK software was included, and the benefits of controlling T80 are lost unless redevelopment for mill design is done. We want to connect existing software with what works. SAG design test for mill sizing works. For this reason, the system is broken. Research time and money is needed to fix it, and no longer a job for one person. It needs a team and funding. The acknowledgements: Professor Babecki at U of T to teach this technology to students, Institute Toms to learn and become fully qualified to design mills and do the test, and finally, Dawson Metallurgical Labs for assisting to develop the SAG design test in 2002 and 3, at Atotech for supporting the development and patenting the SAG mill design technology, which has turned out to be so successful. Thank you.